Hi everyone, my name is Jonghyun, and I'm here to present our paper, FeRG-LLM, Feature Engineering by Region Generation Large Language Models, which will be presented in paper number 805 NAACL 25. This is the joint work with Jonghyun Go, Kyunghyun Park, Dongwon Lee, and Kyunam Lee. To begin with, I'd like to explain the motivation behind our research. Traditional machine learning models, including logistic regression, decision trees, and boosting methods, continue to be widely used in industry because compared to deep learning models, they are easier to interpret, train faster, and work better in environments with limited computing resources. But in reality, data scientists are expected to handle much more than just what's shown on the screen, including all kinds of MLOps tasks. So, being able to offload feature engineering really helps. It saves times and makes the whole modeling process faster. Using large language models helps streamline the whole ML process and lets us explore feature combos we might not have thought of. And that can really boost our chances of getting better model performance. There's been some related work, but most of it relied on cloud-based LLMs which raise data security concerns, not ideal for real enterprise use. Also, they are limited to classification tasks. To address this problem, we used Llama 3.18 billion model and brought its performance on par with the 70 billion model. It even surpasses previous models and can be easily extended to regression tasks as well. And this is our FeRG-LLM, which stands for Feature Engineering by Region Generation. FeRG-LLM uses turn-based conversation to generate newly discovered features for machine learning models. As illustrated on the left side of the slide, when users provide information about their modeling task, the LLM produces the key rationales behind the feature suggestions. Next, the user gives the LLM another prompt, this time asking it to generate actual code for feature engineering based on its earlier reasoning. The model responds with learnable code. By using this output directory, we can automate the entire pipeline from feature engineering to model training and evaluation. So, this is the full framework of our LLM model. Let me explain it in more detail, focusing on two key parts: how we construct data and how we apply feedback learning. So first, we pulled out key information from different documents, things like the data domain, the variables used, and a clear description of the ML task and its type. There's one important point I want to highlight here. The prompt only uses variable names and short descriptions to describe the dataset. It saves analysts from having to manually look through every variable's distribution, which can be really time consuming. Based on that, the model generated not just the reasoning behind the new feature creation, but also the actual Python code to implement it. And since the model gives us executable Python code straight away, the whole pipeline from feature engineering to evaluation can be fully automated. Another key part of our framework is automating the feedback learning process, and we do that using direct preference optimization. To make this work, we ran real-world tests using 8-tabular data designed specifically for feedback. We analyzed the two-step conversation data for feature generation to identify which reasoning behind the feature code contributed more to ML performance and which ones did not. In the final step, we built pairs of preferred and non-preferred rationales and used those to fine-tune the model using DPO. To verify our model's performance, we conducted experiments using a large-scale tabular dataset. For each task, we used XGBoost-based models to perform classification or regression and evaluated whether the features generated by FeRG-LLM actually improved model performance. On this slide, we present our evaluation results on the entire dataset. We set the average AUC computed without feature engineering as our baseline, and then measured the AUC for each method after applying feature engineering. On the classification task, our model outperforms previous methods and performs nearly as well as Llama 3.1 70 billion model. In terms of average AUC, the 70 billion model scores 83.9, while ours reaches 84.79, the highest among all models. For the regression task, we also saw an average MSC reduction of around 5 to 11.5%. In our evaluation study, training the model only on a single instruct answering dataset without the COT style interaction gave an average score of 83.89. Without DPO, the score was slightly higher at 84.50. Both were lower than our full model by 1.06% and 0.34%. Additionally, when we analyzed the embeddings of the generated reasonings before and after DPO, we observed that new semantic clusters either emerged or existing clusters became more concentrated. Let's take a look at a real example where the LLM performs feature engineering and see how its responses differ before and after applying DPO, even when given the same prompt. This prompt focuses on predicting the age group of a given person from the provided record. The parts highlighted in green show the response before applying DPO, while the red boxes show the response after DPO. Although both discovered features are based on the same variables, they result in different feature representations. We can also observe a noticeable difference in the resulting AUC scores. To further assess the FeRG-LLM's efficiency, we measure inference speed by generating 20 outputs for each of the datasets. We previously confirmed that the 70 billion model and FeRG-LLM show similar performance. In experiments based on algorithm 1, completing a feature engineering task required an average of 5.7 responses from the 70 billion model and 7.4 from FeRG-LLM. However, each response from the 70 billion model took at least twice as long as to generate. Taken together, these results indicate that FeRG-LLM is a more efficient model overall. In conclusion, the key contributions of our work are as follows. We developed an LLM that generates high-quality features through a two-turn conversation process with feedback. Notably, operating the model at the 8 billion scales makes it more suitable for environments with security or resource constraints. It can suggest features that human analysts might overlook, and it works effectively with just variable names and descriptions without needing full dataset. By directly producing Python code, it significantly streamlines the entire modeling workflow. This method is expected to contribute to data modeling in AI applications across various industries. That concludes our presentation. Thank you very much for your attention.